Hi, welcome back to the lectures on GPU architectures and programming. So, in the last lecture, if I recall correctly, we have been discussing certain different possible ways in which we can actually implement the matrix transpose operation in a GPU. So, we actually provided two possible options. One was you load by row, store by column, and load by column, store by row, two possible different ways to write that matrix transpose operation, and we saw what are the possible ways in which the computation gets affected and all that. But we'll continue in the same vein, and we'll today actually explore further into how transpose can be accelerated using several optimizations which are possible. So, the first optimization would be, if you remember correctly, in the previous approaches we didn't make use of the shared memory. So, the first optimization would be that you don't directly load from the global memory and then store back into the global memory, but rather you load in terms of tiles into the shared memory and then you write back into the global memory. So, let us get on with the first example on computing transpose operation on matrix while exploiting shared memory optimization. In the program examples that we have provided, in our case we have written the tile dimension and the number of block rows to be equal. So, to be more specific here, let me just give an example what we mean by these two parameters. So, essentially just like our earlier examples where we exploited shared memory, if you remember, it was in matrix multiplication. So, again we will be using that similar concept of tiles, and for that we will define a tile dimension, and in this case we are considering 32 cross 32 size tiles. So, we are considering 32 cross 32 cross tiles, and now when we start talking about the number of blocks and what is the size of the blocks in this specific example that we will be giving, we are again considering the number of rows in a block to be also 32. But if you look into some other similar examples for this same problem, like for example in the source that has been provided, you will see that essentially they will consider the thread blocks to be of size 32 cross 8. Now, there is a reason for that, we will come back to that, and there is also a reason why here we are considering both as 32, we will come to that. Here I just want to make clear that there is a difference in the way you will see the examples done in the references and the way we have done it in the example. So, coming back to our idea of doing a matrix transpose while exploiting shared memory. So, the whole reason for using the shared memory would be what? Like if you have seen the other naive column and naive row approaches, there was either a problem with non-coalesced loads in terms of global memory coalescing, or there was a problem with non-coalesced stores, right. We want to alleviate that problem and use the shared memory to avoid this problem of global memory coalescing either in terms of loads or in terms of stores. So, what we will do is, instead of taking any of those approaches that you load a full row of data from global memory and storing back to global memory into a full column or the reverse, rather we will store at a time a tile of data. So, if we just try to give a pictorial representation here. So, we will divide the entire memory space in terms of tiles, and then we are saying that okay, the first thing I am going to do is I will load a tile of data from the global memory location of the matrix to the shared memory. So, for doing that, the first if we just keep on following our example. So, here we define the tile dimension as 32 cross 32, and we are considering blocks to be also of the same size as tile dimension. That is why the number of rows in the block is also 32. So that would mean in one load operation I have this many number of threads, this 32 cross 32 number of threads which are operating and loading a full tile into a shared memory, right. So I have got this many number of threads here. Now the threads would simply get their corresponding x and y values, that each thread will work with which point in the global memory, the corresponding x and y coordinates. It can just compute from these expressions, right. So consider for example here, so this is a block with ID 00, block with ID 01, block with ID 10, block with ID 11, right. So I have the block ID x dot x increasing this way and block ID x dot y increasing this way, and again inside the block I have thread ID x dot x increasing this way and thread ID x dot y increasing this way. It's a 2D representation here, and so the overall width is of course given by the grid dimension. That is, I mean, if I take this simple example, it's going to be grid dimension in the x direction. That's the number of blocks in the x direction times the tile dimension, which is obvious here, right. So essentially that would be 32 cross 2 cross 32 cross 2. I mean, in each so the width essentially is 64 for this simplistic example I have taken here, right. So now what will happen is, here I am trying to run a loop using which one thread would be loading the values corresponding to its location. For our example, first of all, let's forget this loop. We'll come back to this, and we will also see why this loop is redundant for our purpose. So if I forget this loop, that would mean I can also forget this j here, right. Now look at the code. So essentially all that is happening is, so this I data is your input matrix which has been passed, right. So essentially you have computed for each thread, you have computed xy coordinate, right. So let's pick up some place here. So this is my y and this is my x. So I have computed this xy coordinates, and accordingly this this expression is simply giving me y times width plus x. Of course the width is the grid dimension, that is 2 blocks, and right. So that in the x direction times the tile dimension. So this is my width, right. So multiply y by width plus x, that gives you exactly this location. So essentially you load this thread would load this position from the I data, and it would write into the corresponding tile, right. So let's say this is my tile, and here where is it going to write first of all. So of course now if I look into the corresponding thread IDs for this x, for this thread, this corresponding location. So the way I have computed the x and y values is essentially the offset of the block in the x direction multiplied by tile dimension plus thread ID dot x, right. So this essentially would be my thread ID x dot y, and this essentially would be my thread ID x dot x, that is the offset inside the block, right. So and that is exactly the location, that's the corresponding matching location in the tile in the shared memory where this thread would be loading the value, right. So essentially I have this tile which has been defined, and what the thread is doing is it's doing a load of this tile, right. Now let's come back to what essentially is going on here in terms of the loads by the threads, right. So every thread is going to execute the same code here. It will compute exactly in which location in the tile is going to work with, right. So overall you have this shared memory that has been defined, right, and then when you have this code here, this thread is essentially computing where exactly it is going to load from the input data, and then the next part which is interesting here is that the thread now has to figure out that where in the output matrix is going to write the data that it has loaded into the tile, right. I hope this part is clear to everybody. Now, observe the interesting thing here. You have defined this shared memory, right. As we know, the shared memory is defined in a way that it is transparent to the entire block of threads, right. In this simplistic setting that we have taken, the block size is technically here equal to the thread dimension, that is what we are considering. So, essentially you have a block of threads which are each copying something, one element into the tile, and in that way each thread inside the thread block is actually loading some element into the tile, right. And up to this point we do not have a problem. Essentially all the threads are doing a sequential row access in the global memory, and they are actually writing into the shared memory again using a sequential row access, as you can see from this expression, right. So, up to this is fine. Now, let us look at the next step that we do. Now, the thread has to figure out where it is going to write in the output matrix. So, again let us reproduce the previous figure. Let us say this is my, so a thread block has actually copied this entire tile here, right, this tile, and then it is now identically copied into this shared memory, which is offered as a consistent view to the entire thread block. So, this is my input and this is my output matrix. Now, the way we are going to do this, first thing the thread has to figure out is that okay, I have taken the data from one specific block in the input matrix, the output is going to be written into which specific block, right. For doing this, so essentially if we understand that everything that is inside this block, let's in general write this as a block I comma j, that would be flipped, right. So, essentially now I should be ideally writing into the j comma ith block, right. So, this has to flip. That means technically whatever was my block id x dot y should provide me the new block id in the x direction, right. So, to do this flip of the block, I recompute my x and y using this formula. Let us look at it very carefully. So, I am computing the new x and y values where this thread is going to write. The way it is computed is, so x is now the original block wide is yth position. So, if we just try and understand this, so this is the I comma jth position, let us say. So, here I have a block id x and block id y. So, or if I just keep it same with the original symbols that we are using in the program, let us just call it x comma y. This is my original x comma y. Now, the way we have derived it is, we had a block id x and a block id y, and then again inside it I have an offset of thread id x and thread id y, right. So, the first thing I have to do is I have to flip the block, right. So, that would mean whatever was my original block id x should now start to become my new block id y, right. So, that is why when I am calculating the new y value, I do a block ID x times the tile dimension, right. So, essentially if this was my original block ID x, this will now be considered to calculate the offset of the block in the y direction. So, that is why I do a block ID x times tile dimension, and similarly whatever was my original block ID y would now be used to calculate the offset of the block in the x direction. That is why block ID y is being multiplied by the tile dimension to calculate x, right. But the thing is, when I am calculating the xy position, I do not change the xy coordinates original position relative to the block. Let us understand what it means. So, fundamentally speaking, if this was my xy position, then here the actual transpose position should be what? In order to find that out, I should have actually considered the original x and original y and just use the representations in the opposite, right. So, the x would become the y and the y would become the x, right. So, if I just consider the previous values of x and y which have been calculated following these expressions here, right. So, that is x is being used by block ID x times tile dimension plus thread x. So, this entirely should become by new y. So, that would give me the exactly the position where I am going to place the transpose, but we are not doing that. We will understand why we are not doing that. We just see that can be done in an opposite and hierarchical way. What we are doing is, the first thing we will achieve is, we will just first flip the position of the block. So, if this is the original block position, we find out what is the alternate block position, right. So, when we have figured out the alternate block position, we compute the x and y coordinates of the corresponding x, y values in the original by keeping the relative position here of the x and y same. To be more specific, consider this was your original Tx and Ty. Now, you are in the flipped block here, but in the flipped block, when you are calculating the x and y position, you do not change your Tx and Ty, you consider the same Tx and Ty position. So, from something here you come something here. So, the relative position of this point with respect to this block is same as the relative position of the original point with respect to its own block, just the block's position has been transposed. There is a reason why we are doing that. Now, again look at the code that is following. Again, for our purpose, we are just ignoring the loop. If I ignore the loop, I can ignore the j in the expression that has been given, right. So, now what do you have in the loop? First thing is, even before looking into the expression, consider the scenario if I would have just switched the original x and the original y. Then what would I have done? Inside the tile, I would have just gone through the corresponding position of the threads and loaded them into the corresponding output data by using the completely flipped x and y, right, just flipping the original x and y, but we are not doing it. I will just reiterate. What we are doing is, we are just computing the x and y in such a way that the relative position of the x and y inside the block is same, but the block's original location has been flipped, right. Now, what we are really going to do? So, this is the tile which is containing the data for this block. Now, this tile is going to be written here, right. Now, for a thread which is working in a per thread basis, it has computed using this x and y relation that where is it going to write. So, it is going to write here, right. But the question is, what is here? What is it going to write here? If it is writing the location of the original point, then it is the same data, right, because it has got the if I just go by the Tx and Ty values, then this data is here resident in the tile and I would be writing it using the x and y values, but that is not what I will now do in the operation. Observe this expression very carefully. So, here from the tile, when I am reading from the tile, I am just flipping the position of thread ID X and thread ID Y. If you see our original code, so this is our usual access expression from the input data, right? Of course, you have the Y, that is the row number multiplied by width plus X. But here, and of course, you are writing to the Y, the two-dimensional tile, so thread ID X dot Y is there, and then you have the X for the column. But now here you use the X to check the tiles xth row instead of using Y to go to the tiles yth row. Essentially means that you are not using data from here, the identical location, to write to the flipped block. Because then what would happen? You just change the position of the data with respect to changing the whole block's position, but you don't do the complete transpose. That means you don't just flip the xy coordinate into the yx coordinate, but you actually want to do that, you do it in a two-phase way. So, what you do is, the first part is you change the you flip the position of the block, and then you write into this position using this thread, but from a different position in the column. From where do you write? Exactly. So, when you write, you load data from the tiles txth row and tyth column. So, that would mean you read from somewhere here. So, then you use the earlier x offset to calculate the row offset, and you use the earlier y offset to calculate the x offset, right. Just see the positions are flipped. So, here first thing I do is I use a different value of x and y here. So, essentially the thread will write to the same location in the block, but but it has as a whole flipped the location of the block. Overall the block's location has been flipped, but inside the block I am writing in the same offset location. But then I don't write from the identical location in the tile, but now I flip the input location in the tile. By doing this double flip, I achieve my overall objective of doing an overall flip from xy to yx. Question is, why really am I doing that? Okay. So, now observe now the access patterns that you have. So, from the input data you are writing to the tile. So, all the global loads that you have, the global loads are now all coalesced, right, because you are writing to the global memory with you are reading from the global memory. So, let's observe what are the reads and writes going on in this instruction. So, here you are doing in terms of memory transactions a global read and then a shared memory write, right. Now, the global read is coalesced because you are accessing the global memory row wise consecutive locations, right. So, this is coalesced, right, and then this is some simple computation of x and y. But now, when I am writing to the flipped block, I don't just interchange x and y and make it y and x. Instead of that, I use a modified x and y which gives me the flipped block. Inside the flipped block, I write from the flipped location in the tile, right. Now, why is this a good thing? See, what are the operations I am doing here? So, now I am doing a shared memory load. So, shared memory read or load, right. Now, one may argue that okay, you are loading by column from the shared memory because you are using x here and then you are using the y here, right. Why is that a not so bad thing? Well, this is shared memory. So, essentially you are not having coalescing, but that is from the shared memory. So the load times are very small with respect to the global, so I am okay with this, right. So these are not coalesced, but as a byproduct of this double flipping, now when I write to the global memory, that is also coalesced, right. So I do a global write, which is again coalesced, right. So now the good thing of this two level transpose is that in between I have used the shared memory, but I have used the shared memory a very intelligent way. So if I just rewrite, so this was my input space, and then I am writing to the output space. So I load from a block into the shared memory tile, and then this shared memory tile, which is visible to every thread, I will just repeat inside the block, it will write into the fifth location in the block, right. But again, my write location in the output data matrix is again accessed in a nice row measure fashion. When I read from the global memory, the warps are accessing these consecutive locations in a row wise nice coalesced fashion. So these are all coalesced, these are all coalesced, and the way I am achieving is I don't write the data in such a way that I load here and then when I write I get a conflict. In order to avoid the conflict, I calculate the transpose position of the block, I write in the transpose position of the block, and I write in a coalesced manner, and still for achieving the transpose I write from the shared memories column wise access, right. So I flip in terms of the positions from where I have read, right. So there is a two level flip here, which is helping me to get the overall flip in the position. The first level of flip is with respect to the block ID. The bx and by of the block gets flipped. So from block bx and by, I am writing into the block by comma bx, and when I access the positions, I load data from the shared memory in a column wise fashion. This two level flip helps me to achieve the overall nice coalesced behavior with respect to global memory transactions. But of course, one pitfall, as you can see, that the shared memory will have lot of conflicts here. So if we just use our earlier methods for doing device level profiling, then we can get the statistics. We will see that this is much less if you compare with the implementations where we completely avoided using the shared memory. This is much less, and also if you go to the latency analysis, you see the amount of memory throttling is less, right, because all your global reads and writes are coalesced, and this is one of the basic reasons for that. And if you look into the memory bandwidth analysis, you see that the number of global loads and stores are all small. However, if I look into the shared memory access, the number of shared memory stores are same as global memory loads. Why? Look back to the code, you will see that just like the global memory loads are coalesced, the shared memory writes are also coalesced because they are writing by the row. But when I load from the shared memory, as we discussed earlier, we loaded column wise. Now due to this column wise loading, there has been conflicts, right. Now just we will take a look back into the original code, that why effectively then we did have the loop. Okay. The reason is, in general, when you are writing the code here, one problem the way we discussed is we bypass the loop. If we bypass the loop, then I have very small part thread activity. Now if the part thread activity should not be too small, so that if I am considering very large matrices, right. So to increase part thread activity, one standard way that people follow in the examples is that, okay, you define data, the shared memory locations, in terms of 32 cross 32, but you define blocks of size 32 cross 8. So essentially you have each thread working on 4 consecutive locations or 4 specific locations in a tile of data. So then your data space size remains the bigger 32 cross 32, but you use 4 less number of threads for doing the operation, right. Now, if we are doing that, then the loops will actually be useful. Then as you can see, what will happen is inside this for loop, your iterator j is starting from 0. In every iteration, you are increasing by a block row number. Assume that that number is 8, then your loop really iterates. So you have each thread loading 4 data points into the tile, and then in the other loop it is writing 4 data points into the global memory. Of course, for larger matrices, you can actually use a different implementation. You can have different possible factors here. Just for our simple example, first we wanted to bypass the loop, so we consider tile size and block size of similar. As I am saying that you can have a smaller size block to increase the per thread activity. So if you have a smaller size block, then you have this tile dimension here. You have the j iterator increasing by 8. The loop iterates for 4 times, and each thread loads 4 elements into the tile, and similarly each thread here will write 4 elements into the tile. So with this, we will end this lecture, where we actually show a usefulness of shared memory, how it helps to transpose to coalesce both the loads and stores while doing a matrix transpose computation. In the next lecture, we'll take a deeper look into this. Thank you.